Welcome to Lecture 7 of Engineering Data Analysis. In the next 4 weeks, we will be talking about probability distributions. Again, this is Ian, and we'll start in the next slide, the presentation. Start moving. We begin with discrete probability distributions. We start by defining first random variables to which probability distributions will be applied. Okay, a random variable is a pool or a function that assigns exactly one real number to every possible outcome of a random experiment. The domain of the function is the sample space S, and the codomain of the set of real numbers R. You may refer to figure 1 for the illustration of this concept. The set of real numbers contains integers, decimals, and rational numbers, radical numbers. It does not end left or right of the Cartesian coordinate system. We take the example of the Venn diagram from the topic on sets to illustrate this. And let us illustrate this further with an example, a random experiment observing the suit of 2 cards drawn from a well-shuffled 52-card deck. Again, a 52-card deck has 4 suits, each suit containing or consisting 13 cards from the ace to the king. S is the sample space of this random drawing of 2 cards for 9 times. Okay, 9 times. And so we have the 9 results of those 9 times of drawing. And we now have figure 2 to depict that. The Venn diagram showing the sample space S containing elements of randomly drawn 2 cards. Figure 2 is, again, the representation of that sample space. If with the random drawing of 2 cards, we want to know how many turned up with hearts, we can summarize the output. Okay, the S is given there. We can summarize the output as okay, so the X. The X now is the random variable defining the number of hearts drawn, and X could take on values of 0, 1, and 2, meaning we have a 2-card set with 2 hearts, also those with 1 heart, and those without hearts, without any heart. Anyway, sorry. So in the exact random experiment, a card can turn up with, we have a card that turned up with 2 hearts. We have 2 cards with a heart each, and then 6 turned up without hearts. Again, X is taking on values of 0, 1, and 2. Let us continue with the discussion on the random variables. There are 2 types of such, discrete and continuous, and it could be, well, very obvious how to differentiate between the 2. Okay, even from the mathematical definition from your mathematics, discrete means that it usually takes on distinct separated values. With random variables then, so discrete means taking on a countable quantity of distinct possible values, or even infinite number of still distinct values. With continuous random variables, the variables take on values within a specified interval or continuum. Examples for these two would be as shown. The number of diamond cards in 3 cards drawn from a 52 card deck. That would be discrete. There are no values between the card values, say 9 and 10. Don't have 9.1, 9.2. Likewise, for the cards Jack and Queen, there won't be values between them. For the height and growth rate in height of the PD trees, okay, or plants or seedlings, this is Carnarium ovatum, scientific name of such. Okay, this is in the premises of CBSUA. You have the values of those as continuous, and so you have a continuous random variable. The height and the growth rate can take on any real number value. Well, you go back to the real number definition. For the last example, the number of students entering the premises of CBCA between 6 a.m. to 9 p.m., that would be also a discrete random variable. From the table, we can actually compute for the fraction of the number of occurrences of 0, 1, and 2 heart card drawings. This mirrors their chance of occurrence. But the more you draw, the more this fraction takes on the value of the actual probability of occurrence. Because if you just divide it by for example, the 2 heart cards will take on a value of 1 over 9. That is for just this specific drawing of cards, which is defined as X. But if you continuously do this drawing of cards without end, you will take on a specific probability value, which is definite for the drawing or for the random variable of drawing hearts from a 2-set combination. The probabilities of the 3 events can be calculated if you want 2 hearts to appear, and we have the probability for when X is 0. Okay, that means no heart is drawn. That is the combination of non-heart cards taken 2 at a time. Take note that there is replacement in the card, in the drawing of the cards. Now the number of combinations of the non-heart cards is divided by the combination of the total card quantity taken 2 at a time. And in equation form, that is 39. Okay, that is actually the number of permutations of 39 cards and then without position. So that would be just a combination. The number of permutations of 39 cards is, well, 39 times 38. But since we are not taking into consideration the position, we are going to divide it by 2 factorial, or just 2. And so the number of card drawn for for the event that there are no hearts, then that would be, you have 39 cards because you have 3 suits that are not hearts. So that would be 39 combination, 39 cards taken 2 at a time. And you have at the denominator, the total number of cards, that is 52, taken 2 at a time. And that would be resulting to 1,482 divided by 2, which is 741 for the numerator. And to get the combination of the whole card deck, that is 52 times 51, also divided by 2 for 2 factorial. And the answer would be 2,652 divided by 2, which is 1,326. And dividing 741 by the final answer of 1326, that would result to 0.56. We have computed now for the probability of the 0 heart card, and for the 1 heart 2 cards, we have the solution of taking the combination of the heart cards taken one at a time. And since we have 3 suits that are not heart cards, we have 13. Well, they have to be multiplied by the heart card combination, the heart card um, combination, which is also 13 taken 1. And so we have fractions which are, well, 3 fractions which are the same, and that would be just the addition of the combination of the 13 taken 1 multiplied by another combination 13 taken 1 divided by the total number of possible combinations of the 52 card deck. And that would result to well, it's 507 over 1326. Okay. If you go break that down, 13 taken 1 multiplied by 13 taken 1 all over 52 taken 2 for every suit, that should yield 169 over 1326. And you add that or multiply that by 3 so that you get 507. That's how you result to 507. In reality, you can actually simplify P of x is equals to 1, and I'll leave that as a bonus for the class in the practice exercise. For the probability of the 2 heart card, it only has to be the combination of all the heart cards taken 2 at a time divided by the combination of 52 taken 2. And in simplified form, that is, well, 13 times 12, the quantity all over 2, and that would result to 78. You now divide 78 by the usual number of the overall number of combinations for 52 taken 2, which is 1326, and that would yield a probability of 0.06. I forgot the probability of x is equals to 1 is 0.38. For the probability of x equals 0, that is 0.56. What we can see now here is the tendency of the actual draws, okay, almost relating to the value of the eventual probability of the event of drawing 2 cards and looking for 2 heart cards. We will now go to the concept of the probability distribution with that idea on hand. And the probability distribution is the list of all possible values of a random variable with their corresponding probabilities, which we just have done. They can all be presented in different forms. We have table 1, equation 1, and figure 1 as representations of such or notation of the 2-card drawing from a 52-card deck a while ago, where we want to see the heart combinations or the heart events. Equation 1 is the standard equation for the computations we have just previously done for the x values of 0, 1, and 2. All right, in the next lecture, we will talk about the cumulative distribution function, or CDF, for discrete random variables and expected values of random variables. I will see you then.